Hey everyone, thanks for joining me here. Well, let's talk some redox reactions. This is on page 2. And in order to do the textbook homework, you really got to kind of review this really quickly. We got to go a little deeper into how to assign oxidation numbers and really what they are. So in class, we had just gotten through this reaction here. And depending on what period you were in, I think in one period we balanced it, another period we didn't. So go ahead and pause and balance if you haven't yet. Hopefully you recognize that we need 2 times 3, 6 fluorines there, 3 times 2, 6 fluorines there, 3 coppers, 2 aluminums, 2 aluminums, and now we're all balanced out. So what we're going to do is assign oxidation numbers. And oxidation numbers are a way of tracking the charge. It's not exactly a charge, but I don't want to get too far into what oxidation numbers are at this point. Think of it as like assigning electrons within a compound. Well, where are the electrons at any given time? We need to know something about the charge of the atom or molecule in order to track where the electrons are going. That's a pretty good explanation of really how oxidation numbers are used. First, let's assign 0 to aluminum because aluminum is in its elemental state and it's not a charged particle, so we're going to say it's 0. Same thing with copper over here. We're going to give it a 0 oxidation number. All right, next, let's assign oxidation numbers to these salts. Now we have fluorine and copper. We know that fluorine has a -1 charge as an ion, so it's going to have a -1 oxidation number. Copper, which has a 2+ charge, is going to have a +2 oxidation number. Same can be done over on this side. Aluminum will be +3 because it's a 3+ charge. Fluorine is -1. And notice that the oxidation numbers, they don't necessarily stay the same. Aluminum here goes from 0 to +3. That is a sign that this is a redox reaction. In other words, there's oxidation and reduction going on in this reaction. Let's look at copper. It goes from +2 to 0. Once again, I'm going to actually fix that. There we go. Once again, there is oxidation reduction going on in this reaction because electrons are being transferred. Oxidation numbers allow us to determine where the electrons are going. Well, notice that we have aluminum going from 0 to +3. That is a result of it losing 3 electrons. There we go. And one thing I do want you to note is that because it's a plus, or it's a 2 coefficient, that's actually happening twice in this reaction. Each aluminum is losing 3 electrons twice. And then check out what's happening to copper. Copper is going from +2 to 0. That's because, and that the reason its number is being reduced is because it's gaining 2 electrons. Gain 2 electrons there. And notice that that is happening 3 times. Okay, so now we have a little bit of an idea of where electrons are going. One other thing I want to point out is that if this one's losing 3 electrons twice and this one's gaining 2 electrons 3 times, what's being shown here is that there's a transfer of 6 electrons total. So 3 electrons being transferred twice from aluminum to the 3 coppers, which are each gaining 2 electrons. Now, what do we call this when they gain and lose electrons? We call it either reduction or oxidation. And Leo the Lion Says Grr is an easy way to remember which one's which. Let's start with Leo. Leo stands for lose electrons, is oxidation. And we saw oxidation with the aluminum in the example above. So the example, we saw aluminum. Sorry, I don't know if you can hear the beeping. I just put something in the microwave and it's sitting there beeping at me, and that's going to annoy me, but hopefully you can get through this. So gain electrons, this is the GR of Leo the Lion says GR. Gain electrons is reduced, and the example here is our copper was just reduced. Does that mean copper is always reduced? Nope, sometimes copper can be oxidized, but in this example, it's reduced. Okay, so that was our first redox reaction, reduction oxidation. The one thing that we haven't done now is talked about how do we assign these oxidation numbers. I went through it fairly quickly, but there's a way of doing this. And this chart right here goes through how to assign oxidation numbers. One thing you need to know for this chart is that this chart is actually organized on priority. Sometimes you'll get two conflicting or contradictory ways of assigning oxidation numbers. In that case, you go with the one that is highest on the list. The first item on our list is that free elements, the oxidation number of an atom of a free element is 0. We've already seen this once. Aluminum, which was just elemental aluminum, was 0. Additionally, if we had like fluorine gas has an oxidation number of 0. All right, next, the oxidation number of an ion, a monoatomic ion, equals its charge. So going back to fluorine, let's do the example that we did above. We had aluminum ion, which is aluminum 3 plus. Its oxidation number was +3. If we had sodium ion, its oxidation number would be +1. Okay, so that's the oxidation numbers of those. Now fluorine. Number 3 says in compounds, and so notice it says compounds specifically. Fluorine is always -1. So fluorine equals -1 in compounds. Up here we said is 0 when it's elemental, so that rule still applies. Hydrogen is +1 in compounds. And in compounds, oxygen is -2. So those are just 3 elements to watch for. If you see those 3 elements, assign their oxidation numbers first. And then finally, the sum of the oxidation states for an electrically neutral compound must be 0. What does that mean? Here's an example. Let's say we had H2O2 and we needed to assign oxidation numbers. The sum of the oxidation numbers for this must equal 0. And that's total. So the total oxidation number must equal 0 because it's neutral. So are we going to do oxygen first or hydrogen first? We're going to do hydrogen because it is higher on the list. So hydrogen comes first and it's +1. Well, if hydrogen's +1, what must oxygen be in this compound? Hopefully you recognize that we have 2 hydrogens. Their oxidation state is +1, and so therefore this is +2 total, and therefore the oxygen must have a -1 oxidation state in this compound. Now that does contradict what I just said right here. But to be fair, I told you that we have to sometimes go with the higher priority when there's contradictions. So oxygen usually is -2, but in this compound, its oxidation number is -1. Okay, now we're going to skip this and come back to this in class. It's kind of an important bit that I want to talk about together. And we're going to do the examples A and D in both of these examples. Let's start with this one here. Determine the oxidation number of the elements in each of the following compounds. Well, in total, this has to add up to 0. Keep that in mind. In the end, it is a neutral compound, so it must be 0. Using our rules, we know that carbon is +1. And oxygen is usually -2. Well, those are the oxidation numbers of the hydrogen and the oxygen. We have 2 hydrogens, so that would be +2 total. Here we have 3 oxygens, that would be -6 total. So then what would be the oxidation number of the one carbon? And hopefully you can recognize that this must be plus 4. Because adding up the oxidation numbers, plus 1 plus plus 1 plus plus 4 is plus 6 total, and minus 2 minus 2 minus 2 on the 3 oxygens is minus 6. So in total, it would be neutral. Jumping to D, all right, we have an ion, which means that the total charge on this CO2 must be -1 when we're done. Well, we know that oxygen is -2, and we have 2 oxygens. So if we add up the oxidation numbers, that would be -4. Therefore, what must be the charge on the nitrogen? Well, if the whole compound is -1, this one must have an oxidation number of +3. So what I'm highlighting in pink are the oxidation numbers of the elements. Great. Moving on to the next part then. We want to identify the species being oxidized, the species being reduced, and the number of electrons being transferred. There is a question in the homework, the textbook homework, that asks for oxidation agent and reducing agent. Don't worry about those. We don't need to know oxidizing and reducing agent. It's not even difficult. The question though is what is oxidized and what is reduced. So looking at this first example, we have, that one might be a little too easy. Let's look at B instead. Okay, we have mercury, and it is an ion, so we're going to assign the oxidation number +2 since it's 2 plus charge. Iron here is elemental, so it'd be 0. The mercury here is elemental, 0, and the iron here is +3. If we, so those are the oxidation numbers. If we track what's happening to mercury, it is being reduced from +2 to 0. That would be reduction. And iron is going from 0 to +3. So that is oxidation because it's losing electrons. How many electrons are being transferred? Well, to go from, in the iron example, to go from 0 to +3, it must be losing 3 electrons. But that's happening twice for iron. What we should notice for mercury is that it's gaining the same number of electrons. So we have 3 mercuries, and each of the mercuries is going from +2 to 0. Therefore, it's gaining 2 electrons. And so in total, we have 6 electrons being transferred. Okay, now for D. We have chloride ion, so therefore it's -1 oxidation number. Cobalt ion, +2 oxidation number. All I'm doing is using rule number 1. It's rule number 2. Oxidation number of a monatomic ion is its charge. And then for cobalt chloride, nothing's changed about the cobalt or the chloride because it's still an ionized, it's still an ionic compound, an ionic solid. This would be +2 and -1. Oh, interesting. Chloride goes from -1 to -1. Cobalt goes from +2 to +2. This is not redox because there is no transfer of electrons. It's a good reminder that not all reactions involve a transfer of electrons. Actually, most don't. This is just, so this is a random synthesis reaction. Not a redox reaction. Okay, great. What I'd like you to do is try these for yourself, the ones I'm highlighting here, B and C, and A and C, and once you've tried them, check the notes which is posted on Classroom. You should see the answers there to see how you're doing. Good luck and have a great day.